In this question, we're given a parallelogram with vertices at O, P, Q, and R, and we are told that the side PQ has a midpoint which we've labeled N, and we're told that the side QR has a midpoint labeled M, and we have to show that if we go from one of the vertex at O to the vertex at N, and if we repeat that from O but now to M, then these two sort of segments essentially are going to divide another segment which is linking the vertex at P and at R, and we have to show that the division is such, or the partition is such, that it splits up the segment PR into three equal parts. Okay, so let's see how we could do this. Well, clearly this is rooted in geometry, so we're going to start with a diagram. So we've got our parallelogram OPQR, and then we want to mark M and N on here. So M is the midpoint of QR. So I've got my side QR, and that's the midpoint M. And N is the midpoint of the side PQ. So I've got the side PQ, and there's the midpoint there, right? And in particular, we're interested in segments ON and OM. So I'm going to go to my vertex O, and I'm going to draw a segment from O to N. And then I'm going to repeat that to get another segment from O to M. Okay, so we have the basic diagram for us, but we need to see where these parts are coming from. So we have to insert the segment P to R, and we see that actually the segment ON and OM is intersecting with the segment PR, and indeed there are sort of three sections or three sub-segments, if that's the right word. Clearly, these intersection points are going to come into play in our thinking in terms of solving this problem. So let's label them. So let's label them X and Y respectively. And what we have to show is that PX is going to be the same distance as XY, which is going to be the same distance as Y to R. Okay, so that's the task. So what's our strategy? Well, first of all, we need to get rid of the fact that these are equal. We need to show that. We can't assume that. And our strategy is we are going to work with vectors, and that is because this question gives us no indication of any angles or any lengths, which means doing geometry on this is going to be quite hard, actually. So vectors provide the right sort of language in which we can start to sort of do calculations in abstract algebraic terms, okay? So let's take one of the sides of our parallelogram to be the vector A, and let's take another side of our parallelogram to be the vector B. So the strategy is we're going to write down a description of the vector OX in two ways, and that will give us an equation to solve. And hopefully that would shed some light on what this question is trying to get us to do. And we're going to repeat the same sort of reasoning for the point Y. So in other words, we're going to write the vector OY in two different ways and get another equation and run a very similar argument. Okay, so let's dive in with the calculations. So we want to be able to describe all the standard points on here. So we can just start with describing ON. Well, ON is essentially halfway between P and Q, right? So I can get to N from O, provided I go from O to P and then go from P to N, okay? And P to N, obviously, as I've said, is halfway along the way from P to Q. So in other words, ON is OP plus a half PQ, right? And similarly, OM is obtained by going from O to R and then halfway between R and Q. So OM is OR plus a half RQ, but we need to be able to write these in terms of A and B. So we've got to do some of this work here, right? So PQ we know, which is this thing here, P to Q, is the same vector as the vector O to R, because opposite sides of a parallelogram are literally the same. And likewise, R to Q is actually the same as O to P, which is A, which means that we straight away know what OP, OR are. And we've also just figured out what PQ and RQ are. Okay, we've just done that here. So PQ and RQ. Okay, and so we can stick these in. So OP is basically A, so we stick that in, and then PQ is basically B, so we stick that in, and likewise OR is B, so we stick that in, and RQ is A, and we stick that in. So we've got our description for ON and OM in terms of A and B, and we should also get a description for the vector PR. Okay, so this blue vector here potentially. Well, P to R, we can think of it as going from P to O and then going from O to R. Okay, so PR is PO plus OR, but actually P to O is the same thing as negative O to P, which means that we know what O to P is. That's just A. So I'm going to have minus A and OR is B. So I'm going to have minus A plus B, which is the same thing as B minus A. All right. So we've figured out our key vectors. Now let's hone in on the point X. X lies on the intersection of two vectors. It lies on the intersection of the vector ON, and it also lies on the intersection of the vector PR. Okay. So we can say something, can't we? We can say we must be able to scale ON. So in other words, if I take my ON and scale it down by some scale factor lambda, that will take me to X, right? So that's one way of getting from O to X. And the other way of getting to X from O is actually going from O to P. So that's this part here, OP, and then traveling along PR, but actually we can't travel all the way along PR because then we're going to overshoot and we're going to go past our point X. So what we need to do is we need to scale PR by some amount, right? Such that it's the right amount and it will take us to X. And because we don't know what that amount is, because we don't know how far along X is, in fact, that's what we want to show. We want to show that this is a third of the way along. So what we're going to do is we're just going to say, okay, it's some scale factor. Let's call it mu, right? So I'm going to scale PR by mu, and the mu is going to be exactly what it needs to be such that it will take me to X, right? So in other words, OP plus PR scaled by mu is also another way of getting to X. So I can say that one way of getting to X is the same as another way of getting to X, which means I can have an equality here. Okay. And now we can convert this vector equation into A's and B's because we know what ON is. ON is what we worked out earlier. It's a half B plus A, which is what we have here, A plus a half B rather. And then OP is just A, and PR is what we worked out here, which is B minus A. So we have that there, right? And we can tidy this up. We can essentially expand that lambda into the bracket. So we get lambda A plus a half lambda B, which is what we have here. And this mu can also be expanded into this bracket, which will give us mu B minus mu A. But the minus mu A would combine with this A. So I'm going to get 1 minus mu all in front of my A. And then the mu B is going to be by itself. Okay. So this is the first equation. So onwards with the question. So we're going to repeat this now for the point Y. So we're going to write down Y in two different ways. So we can say Y lies on the intersection of OM and RP. This perhaps should be a vector like so. So if we go back to our diagram to get some intuition on what's happening here. So we've got a scalar multiplied by the vector OM, okay? So OM would be this red vector here, but that red vector here is too big, essentially. So we're going to need to scale it down. So if we multiply it by some scalar, let's call it lambda prime, such that it scales the red vector down, and it scales it just enough so that I can actually go from O to Y and not overshoot. So that's the left-hand side here. And the right-hand side is another way of getting to the point Y, okay? So we're going to have to go from O to R, which is B essentially, and we're going to have to scale RP now going this way by some scalar such that we again don't really overshoot Y. And when we do that, we have OR plus the scalar times by RP. But now think about it, RP, right? RP is the same as PR, but with a negative because it's in the opposite direction. But we figured out what PR was. PR was B minus A. So RP is going to be minus B minus A, which is A minus B, okay? Which means when we stick stuff into our sort of equation here for Y, OM is going to be what we worked out earlier. So we worked out OM to be B plus a half A. So we have B plus a half A. And then RP is A minus B. We've just worked that out, right? And obviously OR is just B because we can see that OR is literally B, right? So we get this here. We get this equation in terms of primes, right? Now we can expand and simplify this, but let's just compare this equation to the equation that we got just before we got our equation 1, right? So this is our equation 1. And let's look at this equation here. I'm going to call this equation the precursor to equation 1, okay, for obvious reasons. Now, this equation is rewritten on the other screen. So this is the equation that I was highlighting earlier on the previous screen, right? So this is our precursor to equation 1. Now compare that to the precursor to equation 2, which is what we have here. Right, so we've got some scalar, and then, well, I've got b plus a half a, I've got a plus a half b, I've got b here, I've got a here, I've got a minus b here, I've got b minus a here. So in other words, these two equations are literally exactly the same. The only difference is the a's and the b's are swapped, right? And rather than having lambda and mu as my scalars, I've got new scalars that I'm calling lambda prime and mu prime, okay? Now, for obvious reasons, we can't label these lambda and mu because that will then be putting into the question by hand the position that the scale by which you have to scale sort of p to r to get to x is the same that you've got to scale r to p to get to y, and we don't know that's the case. We need to show that's the case, so we certainly can't assume that. So we certainly need two separate scalars in each case, okay? But the point is, so we know that if this was what we got from our equation 1, then our equation 2 is going to be exactly the same as equation 1. The only difference is going to be our lambdas and mu's are going to be replaced by lambda primes and mu primes. And every time I had an a in a place in equation 1, I'm now going to get a b. Okay, so if I had a b in a place in equation 1, I'm now going to get an a. And likewise, if I had an a there, I'm going to get a b. And if I had a b there, I'm going to get an a. Okay, so we've managed to write down our equation 2 just by using some sort of basic symmetry arguments. And now we have to solve these simultaneously, essentially. And what we can do is from equation 1, we can equate coefficients. So we can say, well, if this is equal to this, right? So the coefficients of A have to be the same, which means lambda has to equal 1 minus mu, which is what I have here. And then equating the coefficients of B, I can say a half lambda must be equal to mu, which is what I have here. And of course, if I get a set of equations from equation 1, I get the same set of equations from equation 2. And if you want to verify, you can just verify by saying that equating the coefficients of B, I'm going to get lambda prime is equal to 1 minus mu prime, which is what I have here. And equating the coefficients of A, I'm going to get a half lambda prime is equal to mu prime, which is what I have here. So now, for this system, we've got two equations, two unknowns. For this system, we've got two equations, two unknowns. We just solve each system, okay? So the first one, we see that actually I've got a minus mu on the right-hand side and a plus mu on the right-hand side for each of my equations, respectively, which means that I can just add these two. And when I add these two, the mu on the right-hand side is going to cancel, and I'm going to end up with just a 1. But when I add a lambda to a half lambda, I'm going to get 3 over 2 lambda on the left-hand side, which I can then just rearrange to say lambda is 2/3, okay? So since we've figured out lambda, we can also figure out mu. Mu, we can essentially stick into this equation here and say mu is going to be 1 minus lambda. So if lambda is 2/3, then mu has to be 1/3, okay? So we've got our lambda and mu for one of the points. Now let's figure out the lambda prime and the mu prime for the other point. Well, we know that they're going to be exactly the same because the system of equations is exactly the same, okay? So you can run through the algebra if you really want, but lambda prime will turn out to be 2/3 and mu prime turns out to be 1/3. So what does that mean? Well, what that means is, if you think carefully, mu and mu prime were actually what we were scaling PR and RP by, respectively, right? To get to the point X and Y, respectively. And we've just shown that the scale factor by which we've got to scale PR, mu, is the same as the scale factor by which we've got to scale RP, right? Which is mu prime. So they both turn out to be 1/3, which means that if I was to consider the ratio px is to xy is to yr, then px would be, this sort of segment here, and yr would be this segment here. But obviously, the way we're thinking of this is we're taking the vector PR in the first case, and we're scaling it by 1/3 to get the vector px, right? So that's where this third comes from. And then for the other case, which is y to r, we're thinking of it as going from r to p, which is this thing here, but we're scaling it by 1/3 again to get from r to y. So this segment here has to be 1/3 in comparison to the entire blue segment PR, right, or RP. So we've got these two ratios. we don't know what the ratio on the inside is, but actually we can figure out what the ratio on the inside is, because if I'm telling you, or if the maths is telling us that actually px is a third and yr is a third of the entire blue segment, then the thing that's left has to be the other third, right? It has to be the remaining third. So in other words, px is to xy is to yr is in the ratio a third is to a third is to a third, right? Which is exactly what we wanted to show. So in other words, we wanted to show that these three segments are equal. And indeed, because the ratios are equal, we can just multiply through by 3 and we're going to get 1 is to 1 is to 1. And so we've managed to answer this question. Okay. I hope this has been useful. If it has been useful, then do consider subscribing.